Yeah, hello, this is the first video series on differentiation of inverse trigonometric function. So we're going to be differentiating y equal to sine inverse of x over a and y equal to cos inverse of x over a and y equal to tan inverse of x over a. So we're going to be finding its differential here, and let's start with the first one, which is y equal to sine inverse of x, there's a bad a there, of x over a. Yeah, then the first thing to do is to take the sine of both sides, so this sine inverse cancel out here. So we have sine of y equal to, so if we take sine of this side, we just have x over a left, so we have x over a. Then we have to differentiate this. Of course, if you differentiate sine of y, you have cosine of y, but since you differentiated the dependent variable, you need to add the y over the x to that side. So we have now if you should differentiate, of course we can simplify this to be 1 over a, then x. Of course 1 over a is a constant, of course we'll still have 1 over a, and if you differentiate x, you just have 1, so you have this times 1, or you could just leave that out. Then we'll have to make dy dx the subject of the formula here. So we have dy over dx is equal to 1 over a, 1 over a cosine of y. Now, of course, we said sine of y is equal to x over a. So let's try to draw a right angle triangle there. So this angle here is y. This angle here is y. So we have x over a. Now the x is the opposite side, so we have x, since it is sine, so here should be opposite over hypotenuse. Opposite over hypotenuse, which is a. That means this side, we can calculate this side using Pythagoras theorem. That means here should be a squared minus x squared. Then we can rewrite this, the whole of this, as 1 over a. Now cosine of y from here, cosine of y, let me use another color. Now cosine of y, that is cosine of y from this diagram here. Cosine of y will be adjacent over hypotenuse. Adjacent over hypotenuse, which is a. So we have adjacent over hypotenuse. Of course the a's cancel out, so we now have 1 over square root of a squared minus x squared. So whenever you differentiate sine inverse of x over a, you always have 1 over the square root of a squared minus x squared. So here is it. And so let's now use the same method to differentiate this one here, and let's clean this up a bit. Let's clean this up a bit. Alright, so we now have as for this one, now we have y equal to cos inverse of x over a. So I said the first thing to do is to find the cosine of both sides, so that this cos inverse here cancel out, leaving x over a. So we have cosine of y equal to, now cosine of the cos inverse of x over a is just x over a, and we can write x over a as 1 over a, then x in bracket. Then we now have to differentiate both sides. Now if you differentiate cosine of y, you have negative sign of y. Now since you differentiated a dependent variable, you have to put your dy over the x over there, and then if you differentiate x, you just have 1, then 1 times 1 over a is still 1 over a. So we have then we now make dy dx the subject of the formula, so we have dy over dx is equal to negative 1 over a sine of y. So let's figure out what sine of y is drawing a triangle. So let's draw a triangle over here. Let's use another color. This is yellow. So so we have y here, then so we have cosine of y, so we have y there. Of course, since it is cosine, it is what adjacent over hypotenuse. So adjacent is x, hypotenuse is a. And we can calculate this side using Pythagoras theorem by saying is a squared minus x squared. So therefore we could write the expression for sine of y there. So from there we can say sine of y from here will be opposite over hypotenuse, opposite over hypotenuse, which is a. Then we have to substitute this into this equation right here. So we have minus 1 over a. Now sine of y is all of this here, so we write a squared minus x squared over a. Of course, this a cancel out, so we have negative 1 over square root of a squared minus x squared. So that is it. Of course, it's the same thing as the differential of the sine inverse of x, but just that the negative sign differentiates it. So if you should differentiate negative sine inverse of x over a, you have 1 over square root of a squared minus x squared. But if you should differentiate the cos inverse of x over a, you have negative 1 over root a squared minus x squared. So lastly, let's clean that up again. And hopefully you could even try this. You could pause the video and give it a try. Alright, let's solve it. So we have y equal to tan inverse of x over a. Now of course we have to find tan of both sides, so we have tan of y is equal to, if you take tan of the tan inverse of x over a, we just have x over a left, and we could write that is equal to, you could write that as 1 over a times x. Then you have to differentiate both sides of the equation. So if you differentiate tan y, you have sec squared y, then you have to put your dy over dx equal to, differentiate x, you just have 1, then 1 times 1 over a, we have 1 over a. So we have to make dy dx subject to formula right now. So we have dy over dx equal to 1 over a sec squared y, sec squared y, that y looks like x. Let's clean that up. Alright, so from this expression, from this equation, we need to figure out sec squared of y. So let's draw a right angle triangle here. This is a color. So we have a right angle triangle. So here is y. Then of course, since this is tangent y, so this is what opposite over adjacent. So we have opposite, which is x over adjacent. That means this side over here can be calculated using Pythagoras theorem, and it is a² plus x². Now sec, of course, note that sec y from this diagram here is something as saying 1 over, or generally sec y will be something as 1 over cosine of y. So we have, no, cosine of y from here is a, which is adjacent over hypotenuse, but since we have inverse of it, so we have hypotenuse over adjacent. So sec y now will be hypotenuse, which is root of a² plus x² over adjacent. So we have a, so that is sec y. Now sec squared will be everything here, then squared. That means let's rewrite this, but let's use this instead of sec x. Let's use black this time around. So we have dy dx, dy over dx as 1 over a. Then we have sec, so I have a² plus x² over a. That's about it there, over a. Then everything squared. Of course, since we have a² here, so this a we cancel one of this a here, so we now have a. So we have, from this we should have that a at the top. Then we'll have, now if we should take square of this square root, of course that square root sign we cancel out with this. So we now have just a² plus x². So whenever you differentiate tan inverse of x over a, whenever you differentiate the tan inverse of x over a, you should have a over a² plus x². And thank you very much, and we'll be right back with the second series on using this to solve integrals and the other differentials. And make sure to like and subscribe to my YouTube channel. Thank you.